Hi again. So we're gonna talk in this part about the finite differences method. We need to make a very detailed introduction and then to extend a bit the explanation before we go in the details of the course. Uh, in fact, the idea is to find a solution to a partial differential equation. What you have done last year, you calculated numerical solutions to differential equations. I need to recall what we have done last year so you can understand really what I'm doing in here. Okay, so uh, last year I will take some place on the board here. So last year you had an equation like I don't know, y prime plus ay equals something. Okay, and the idea was to find a numerical solution, which means try to find the value of the function y, which is solution to the equation, at some given points. The difference between this numerical solution or a numerical solution and an exact solution is that the exact solution is a function given explicitly. Yani you have y is equal to cosine x plus exponential x plus whatever. Okay, this is an explicit solution. The numerical solution is a solution given at some points. So we don't know the function explicitly, but we know that the function has a given value at a given point, a given another value at another given point, etc. Okay, so what you have done last year is the following. You replaced y prime in this equation by the explicit approximation of the derivative. So instead of y prime, we wrote yi plus 1 minus yi over h plus ay. Let's say it was equal to 0 to simplify. Okay? Or no, it can be equals to f of xy. X being the variable, y being the function of x. So, having said this, then you conclude that yi plus 1 is equal to h a y with a minus plus h f of xy plus yi, which is equal to yi plus h, so plus h f of xy okay, minus h ay. I put it this way to rearrange the h, but instead of putting y, we'll put a yi in here. So our equation is completely discretized, which means that I will replace y by yi, x by xi, and y by yi in here. So again, here we will have yi, xi, yi, and yi. Okay, and again, that's why it will be written now. It's yi plus h f minus a yi. Okay. What I'm writing in here, just it's a form of writing yi plus 1 function of h and yi and xi eventually. It depends what's the expression of f. The idea is that if you have this kind of expression, it means that if you have xi, yi, and h, you will be able to calculate yi plus 1. Let's take it step by step. It means that if you have an initial term, an initial term for y, it means that you know that every differential equation should be combined to an initial term, so it can have a unique solution. So for example, sometimes you have like something like y of 0 equals to 1. Okay, this is the initial term. It means that if your aim is to find a function whose shape should be like this. We don't know the shape in advance, but it should be something like this. Okay, let's say if we need to calculate numerically the solution of this function, which means that we need to find data points at which we have to know the value of the function. Okay, so the data points we have, we want to use to calculate the value of the function at which we want to calculate the values of the function, are chosen by us. So it's for us to choose which xi's we want to use to calculate the corresponding yi's. Yani, we say that, okay, we will start by x0 equals to 0, let's say, and then x1 will be equal to 1, x2 will be equal to 2, x3 will be equal to 3. That's why our step size is 1 at each time. Okay, so we have a step size of 1, and we start by x0. The thing is that at x0, we already know y0. y0 being the value of the function at x0. Okay, let me point out something, that this is true because at x0 we know that the value of the function is equals to 1, so we set our y0 to 1. But now we need to calculate y1. y1 is not f of x1, because y1 is, and be careful, is an approximation of f of x1. F of x1 is the true value, and y1 is the approximation value. Okay, so now we need to calculate y1. I will say it again. y0 is equal to f of x0, because at y0 it's given in here. We have y of 0 equals to 1. We have the value of the function. So this point here is an exact point. There's no error in this point because we already know the value of the function at this point. But the value of the function at this point, at x1, we don't know it, and we will approximate it. So how do we do it? We say that, okay, using the formula that we obtained in here, we know the xi, we know the yi, and we know x0, we know y0, we know h, how كل known values, يعني we can calculate y1. So y1 will be somewhere, let's say will be somewhere. The screen has moved. So it will be somewhere in here. Okay, I will put it maybe in blue, so we say that it's an approximation. Okay, then having y1, we add x1, we already know it, h, we already know it, we have these three values, we will calculate y2. So y2 will be somewhere in here. So finally, when we finish, we will have these points, these blue points, that will represent the approximation function. So the approximation function might be something like this. Like this and this. Okay, so it follows the function. It's, of course, there is some error in here, there is some error in here. Okay, so all this you did it last year, and this is what we call the discretization. We discretized our equation so we can calculate the function point by point for some given points. Of course, when functions are more complicated than this red one I drew in here, we're not sure if we are doing a good approximation, and it depends which approximation you used in here to approximate the first derivative. If you use an explicit one, an implicit one, or etc., we might have problems about the stability of the solution, if the solution goes to infinity or not, etc. So this is what you have done last year with differential equations. Okay, I think that's everything I wanted to say in here. It's very important to understand that we are calculating yi's step by step, and it's very important also to make the difference between this kind of schemes, this kind of calculations in here, and the iterative methods, because it's an iterative procedure. We are calculating yi plus 1 function of yi, but it's not an iterative method in the sense that each time we calculate a step, we are moving closer to the solution. For example, when you used to make the Newton method to calculate a zero of a function, you used to calculate that if you start in here, you make the tangent, for example, somewhere in here, you have a point, then you make the other tangent, and then you are coming close to the solution. And this kind of methods, each step I do further, I will have a better approximation, or I'm moving closer to the solution. But in the differential equation, in this kind of procedures in here, no, that's not the case, because each time I'm doing a step, I'm calculating one more point of the function, and finally, to obtain the function, I'm combining all the points I have calculated. Okay, this is everything I wanted to say. Now, in this case, in this chapter, we'll be trying to solve partial differential equations. It means that in the equation now, we have the derivative of y with respect to many variables. We will start by an example taking the heat equation, okay, which represents the diffusion of the heat in some material, for example. Okay, I will write it down. It's delta T u of Tx minus kappa, which is a constant, d2xx u of Tx equals f of Tx in 0 T times 0 1, with u of T0 equals to 0 for all t in 0 T, u of T1 equals to 0 for all t in 0 T, u of 0 x equals u0 of x for all x in 0 1. Okay, I'm writing it down so we can make some explanations about this example. So if you look in here, this is the main equation. Okay, in this equation we have the variable or the function to find is u, but u is given function of Tx. So we have two variables, and what we see in the equation is two kind of derivatives. We have the derivative dtu, which is the derivative of u with respect to the first variable t, and then we have the t2xx of u, which is the second derivative of u with respect to x. Kappa is a constant, and on the other side we have f of Tx, which is called the source term, which is usually a given function. Okay, so if you calculate this equation, the solution u will be representing, as I said, in some cases, the diffusion of the heat in a material. So if you have an iron plate, for example, and then you apply heat on one side of this plate, and then the heat will diffuse inside the plate. So this movement of the heat is represented by the solution of this kind of equations. F of Tx might be representing the source term, so that the applied heat or the initial heat across the plate, etc. Okay. Type. What's given in here are source terms that we need to calculate the solution, the unique solution. And why do we have three conditions, or maybe more? We'll understand these conditions now. But because we have many derivatives, so we need more givens so we can find an exact solution. Otherwise, you will have constants when you integrate. U of T0 is equal to 0. It means that if x is equal to 0 and if t is anything, your function is equal to 0. So if we want to understand more, I will read the equation differently. I will say that let t, the variable t, be representing the time, okay, and x be representing the space. And we have one variable in space x, we don't have two variables, we don't have x and y. So our problem might be, for example, a linear, or let's say a bar like this, okay, which is in one dimensional bar, and then we are applying some heat in here on this at this point. So if we want to draw the function that represents the value of the temperature at each point, maybe in the maybe at t equals to 0, okay, it will be something like this. We have the heat applied at the first point, and then at the end point here the temperature is still 0. But at t equals to 1 second, we have the heat applied at the initial point, it's still in here, but then the heat is propagating, so the temperature is going up in here maybe a little bit, and then it's going back down to 0. If we move forward in time at t equals 5 seconds, for example, okay, we might have the function will be like maybe like this, okay, and maybe here it will not be 0 anymore, it will be higher than 0 at the end. Let's make it a little bit higher, it will be like this, not 0 anymore, okay. So what we have here is at each time step we have a function that varies in x. يعني هون for x equals to 0, and here it's for x equal to the final point, it's 1. هون كمان 0 1 0 1, and at each time step we have this function that varies in x. So this is how we want to read the equation. So when I say u of t0 is equal to 0, it means what? It means that your function when x is equal to 0, even when the time changes, it will be always 0. يعني at this initial point here, we don't have a heat applied, we have the value is always equals to 0. This one in here means that at this point in here, the value is always equal to 0, even when t changes. But u0x, so when the time is equal to 0, we have a function in space which is u0x. Okay, so the problem might be again something like this. This is the bar, let's say, and the initial function u, the initial distribution of the temperature, is given by what's in here. It's u0x equal a function u0x. This function is given. It might be a cosine, a sine, whatever. It's a function given. It might be, for example, the distribution of the temperature on this red bar in here. I will make it in blue, for example. Might be like this. But it's also wrong. Why? Because this initial function does not satisfy the two conditions which were in the beginning, which are that at x equals 0 and x equals 1, the value is equals always to 0. So again, so I will change it to make something more consistent. So it should be here it's equal to 0, here it's equal to 0, and inside we have a function, okay, a given function. يعني it's like if we have a bar heated from the middle for this kind of functions, or it might be also like this. I will take another example. It might be like this, 0 in here, very high in here, and then 0 in here. So it's heated in the middle, and then in some time the heat will be more distributed across the bar, and if we are keeping both sides equal to 0 because we are freezing them with some kind of equipment, so the temperature will be more distributed, will be more like this. Okay, so I think you understood now these conditions, what does they mean. هلا, to solve this kind of equations, we will discretize the equation. So we will use approximations as we did in the differential equations. We will use approximations of this term, which is a derivative, and this term, which is a second derivative. We make the approximation of the first derivative in time with one of the methods we already learned, explicit, implicit, or centered approximation. We make an approximation of the second derivative in x with one of the methods we learned as well. And then we will see what kind of methods we used, are they compatible in time and space, and what kind of results we'll obtain. Okay, so this will be the topic of my next video.